Okay, so hello and welcome everyone to the week 8 live session on the course Experimental Biochemistry taught by Professor Shagata Dasgupta and Professor Shomode of IIT Kharagpur. I am Srijan Sen and today I will be I will be taking the live session of the lectures which were taught to you in week 8 and also discussing with you a few questions which will help you in solving the assignments and the exam which is coming on. Okay, so I'm sharing my slides with you people. I guess my screen is visible to you all. So let us start. So in today's class we would be discussing mostly about enzyme kinetics. So we will be seeing the different types of what is the role of an enzyme in a reaction and what an enzyme does and what kind of kinetics does enzymes play in certain reactions and all, and what different applications of this enzyme kinetics will be discussed with you people. So what are enzymes? So enzymes are basically proteins that increase the rate of the reaction by lowering the energy of activation. So enzymes do not actually take part in the reaction, but what it does is that it has an indirect role in it. It increases the rate of the reaction by decreasing the so-called energy of activation, and thereby it increases the rate of the reaction. So they basically catalyze all the chemical reactions which takes place in our body. So our body has different enzymes, so which plays different role of catalysis inside our body. So these enzymes are neither altered nor consumed during the reaction. So as I was saying, they do not have a direct role to play in the or by taking part in the reaction, but it just reduces the energy of activation and increases the rate of the reaction. So these enzymes can be reused from time to time because they are neither altered nor consumed during the course of the reaction. So these enzymes are basically, we can call them as the biologic catalyst because they have certain shared properties with that of the chemical catalyst. So it is that the enzymes are neither consumed nor produced during the course of a reaction, which the chemical catalysts also have shared property with them. And the second one is that the enzymes do not cause reactions to take place, but they greatly enhance the rate of the reactions. They do not cause the reactions. Okay, that would be so how they enhance the reaction. They means in the absence of these enzymes, the reaction is much slower, so they enhance the rate of the reaction by decreasing the so-called energy of activation. Okay, so they alter the rate but not the equilibrium constant of the reactions that they catalyze. Also, they have some differences. There are some differences between the enzymes and the chemical catalysts. The first one is that, as mentioned, that enzymes are proteins and they are highly specific and produce only the expected products or the products that we need from the reaction, and which we also call the substrate. That is, there are no side reactions. Okay, so also they are highly specific, which is very important in biologic reactions and all. So enzymes also show a high specificity towards one substrate or exhibit a broad specificity using more than one substrate. And enzymes usually function within a moderate pH and a temperature range. So these are some of the features of characteristics means enzymes, which differs from that of the chemical catalysts. Now coming to this is a cartonic diagram. So this is of a normal reaction, and the other one is an enzyme catalyzed reaction. So what happens in the normal reaction, we have usually, not for all reactions, but so why do we require enzymes? When the energy barrier is very high, we need to lower the energy barrier such that the reaction gets formed. Okay, so just this is a frog who wants to jump across this barrier and get into the pond, you can say. So what happens? So here you can see that there are a large number of stones or bricks, which actually is making the frog difficult to actually cross such a high barrier. Okay, so what happens, the reaction becomes slow and lesser number of reactants will be converted to your products. It does not mean that when the energy is high that no reactants will form products. There is nothing called 100% reaction not happening or 100% product formation is happening. Okay, so because there is an equilibrium in between them, so when the energy barrier is very high, you can see that only a few frogs will be able to cross such a high barrier. Whereas what happens when enzymes, what the enzymes do, it just breaks a few of your stones and just reduces the barrier, so that higher number of frogs or the frogs can easily cross the barrier and move into the ponds. So what happens in a normal reaction is that the reaction proceeds at a slow rate due to the prohibitive activation energy threshold. Whereas when enzymes play a role, the reaction proceeds significantly faster, and so the reaction proceeds significantly faster, as you can see that the activation energy threshold gets reduced. So now coming to the concept of free energy. So you can see that more free energy means your thing is less stable because of the greater work capacity. Okay, so as the free energy gets decreased, the direction of the spontaneous change is delta G less than your 0. And when you change in the direction of the equilibrium, it can be, it indicates that you can perform your work. So when the free energy, what happens is that now this is a more energy state, that is less stable, that is it is acquiring a greater work capacity. So now here it happens that the free energy gets reduced, that is now the person or those number of molecules have reached a more stable state, and thereby it is actually lowering your work capacity. Fine. Now, when the free energy of a reactant is greater than that of the product, then it happens that the free energy of the reaction is negative, such that the reaction proceeds spontaneously. So del G is less than 0 over here. Okay. So here you can see that in the diagram 1, so the reactance is greater than that of the product, so it will reach very easily and the reaction becomes spontaneous. Now if the free energy of the product is much greater than that of the reactant, that is the case which is vice versa, then the free energy change of the reaction becomes positive and the reaction finds it's very difficult to occur spontaneously. However, you can see that the reverse reaction becomes much more feasible or spontaneous. Okay, because from the product to the reactant it becomes much more easier, but we know that what we require from a reaction is all about the product. So here the del G becomes positive and the reaction, you can tell, is slow or the reaction does not occur at all. Now there are different components of an enzyme. So first of all, what we have is an apoenzyme. So an apoenzyme is the inactive part of an enzyme, that is we can call as the protein portion. Now why is it the inactive part because it lacks your coenzyme or the cofactors. So these cofactors are the non-protein portions which actually are important in activating your protein or your apoenzyme. Now when this apoenzyme mixes with your cofactors, there are different cofactors which act as activators of your proteins, and these are basically your non-protein portions. So when this thing happens, your apoenzyme and your coenzyme joins together to form a holoenzyme, which we can call as the whole enzyme or the active part of an enzyme. That is, your enzyme gets activated. So when a protein or a cofactor meets your protein, an inactive protein, it gets activated, giving a holoenzyme. And then there is the role of the substrate, which comes and plays a particular role. So there are different cofactors which are present or are acting as your activators. So among these, we especially have your essential ions. There are many ions like your activator ions, which are loosely bound but are playing a role in the activating your proteins. And also there are metal ions of metallozymes, which actually tightly bind to your apoenzyme. Also at the same time, in the category of cofactors, we have your coenzymes. So these coenzymes can be your co-substrates which loosely bind to your protein. Also there are some prosthetic groups which tightly bind to your protein. So these are the different classes of cofactors which we have, which act as the activators, and these are basically your non-protein portions required for your protein portion, which is your apoenzyme, and then your entire enzyme gets activated. So another important term which we need to know when we speak of enzymes, and that is your active site. So it is that part of your enzyme where the substrate gets attached and plays a role. So here, like this is the substrate, so this part is your active region or your active site where your substrate is going to bind and activate your enzyme. So that is the area of the enzyme where the substrate or gets attached in order to activate your enzyme, and then your enzyme becomes functional. So like this is your enzyme, and then this is your catalytic site where your reaction is going to occur, and then you have your substrate, and this is your binding site where your substrate is going to bind, and there is the catalytic site where your reaction will occur. So the binding site is responsible for holding your substrate in place. The catalytic site is where your reaction is going to occur, and the substrate is going to bind into the catalytic or the binding site, your binding site, and then the reaction will proceed further. So when the substrate is entering the active site of the enzyme, then the enzyme sometimes changes shape slightly as the substrate binds. So thereby you are getting your enzyme substrate complex, and then what happens is that the enzyme substrate forms your product. So then you get your enzyme product complex, and after this what happens, the role has been played, and then you get your product. So first the substrate enters where the substrate will be converted to your product. So it comes and binds to your enzyme, and then the enzyme actually plays some kinds of roles, and it changes the shape, and this substrate gets converted to your product in that attached manner. And after that the products gets released into the environment, and you get your products, and the enzyme remains in its original form. You get back the enzyme. So this can be this is a characteristic of the enzyme, that these can be reused, and these enzymes do not directly play a role in your reaction but actually enhances the rate of the reaction. Now coming to an important theory of enzyme kinetics. So we basically have two theories of enzyme kinetics. Before we speak of enzyme kinetics, these theories are important to be understood. So basically there are two theories. One is your lock and key model theory, and another one is the induced feed model theory. So first is the lock and key model. So what happens here? So in this kind of model, or the lock and key model of enzyme action, the activator site, the active site has a rigid shape. So it maintains a particular shape, and only the substrates which actually matches that particular shape can only fit into such an enzyme. So the substrate becomes the key of such a model, and that fits into your active site of the enzyme. So here your substrate becomes the key and the lock is the active site of the enzyme. So this is basically was used previously and is an older model, because first of all it faces some of the drawbacks, is that not always will your substrate have that particular shape that it can always fit in. There are very less probabilities that the shape of your enzyme, that the active site of your enzyme having a shape, will match with your substrate, and unless this situation occurs, then there is a very less probability that you would be able to actually perform such a enzyme kinetic and perform a reaction. So this is one of the drawbacks, and this was used previously. So a much modern technique is that is your induced fit model. So here the active site is very much flexible and is not rigid, which actually allows the enzyme to change its shape based on the substrate. So if your active site has a square shape but your substrate is a circle, say, so it won't be fitting, but your active site, the enzyme would change its active site in such a manner that the substrate can fit into it. So what it has, so here the active site is flexible and not rigid. The shape of the enzyme, the active site and the substrate adjusted it to maximize the fit, and thereby it improves the catalysis. And therefore, because of such a characteristic feature of this model, it actually enlarges the range of substrate specificity, and thereby actually people are nowadays using this kind of model for such reactions, for performing the reactions and studying the enzyme kinetics. And this model is much more consistent with a wider range of enzymes. You can know why, because your enzyme can actually modulate itself based on the shape of the substrate. And in any ways, the enzyme, when it reacts with the substrate, it is forming an enzyme substrate complex. And after this, the enzymes, so there are different phases. One is where you have the substrate and the enzyme separated, like this, where you have the enzyme and the substrate separated. Then after it binds, it forms the enzyme substrate complex, and after that you get the substrate changes to products in the presence of your enzyme, and after that the products gets released. So here the first your enzyme substrate complex is formed, and after that you get your enzyme product complex, and then whatever the product is, this can be actually released out. So here we have the different classes of enzymes according to your IUMB system. Okay. So based on this IUMB system, what we have is that we have the different classes, one of which is the oxidoreductases, which play important roles in the redox reactions. Then we have the transferases, which actually are important in different, when you have to move some, say, some molecules from one region to another, or from one place to another. So these transferases actually play an important role. Then we hydrolases, which in which water is plays an important part in it. Then we have the lyases, isomerases, the ligases, and the translocases. So these are the different classes of your enzymes based on such system. So IUMB has classified them. So it is the International Union of Molecular Biology and Biochemistry. Okay, so these are the different classes. We need to just keep in mind these names and all, and what these enzymes actually play a role in. Now coming to another important term, which is your catalytic efficiency. Okay. So catalytic efficiency is that mostly enzyme catalyzed reactions are highly efficient, and proceeding from around, you can say, 1000 to 10 to the power 8 times faster than your uncatalyzed reaction. So what happens is that the enzyme molecules are capable enough for transferring a lot more of your substrate molecules into the product per second. So the number of molecules of substrate which are converted to product per enzyme molecule per second is called as the turnover number. So you can see that higher the turnover number, higher will be your catalytic efficiency, because the enzyme would be efficient enough to actually convert your substrate into the product. Okay, so thereby the catalytic efficiency increases around say 10 to the power 3 to 10 to the power 4 or to 10 to the power 8 times faster than your any uncatalyzed reaction. So this is an important term which you definitely need to keep in mind, that is your turnover number, because your turnover number is that the number of molecules of substrate which is converted to your product per enzyme molecule per second. Okay, right. Now there are different environmental factors, one of which is the optimum temperature, that is the temperature at which the enzymatic reaction occurs fastest. And also there are some temperatures in which your enzyme gets activated. So we basically store enzymes mostly in minus 20 degrees centigrade, but they get activated at different temperatures, like your fusion protein, your fusion enzyme which we use for performing different PCR reactions. Also sometimes you have heard of the enzyme named Taq polymerase in your PCR reactions. They get activated usually at, you say, 72 to 70 degrees centigrade. So these are the temperatures in which certain enzymes gets activated. So a particular temperature becomes very much important for the activation of these enzymes and the faster enzymatic reaction to occur. And then you must have heard about different restriction enzymes, then your ligases which are activated at lower temperatures, say 22 or 37. Okay, so there are different temperatures which are optimum for the functioning of different enzymes. So the optimum temperature is another factor which is very important in the role of enzymes or an enzyme to play a particular function. Also, pH plays an important role, because pH affects the rate of the enzyme substrate complex. So most enzymes have an optimum pH of at around 7. However, some prefer acidic or basic conditions, like you have an enzyme which has an optimum pH of 7. So it will basically take over your neutral proteins or your substrates and all. But say your substrate is negatively charged and you want your enzyme to be a bit positively charged, so then you can actually what you do is lower down your pH and then make your enzyme a bit more positive, and then your substrate is negative, so it can bind much more tighter. So in this manner, depending on what you want the pH to be and depending on the substrate you are going to use, so depending on that you can actually vary the pH and play around with the pH such that you get better binding. So you can see here that pepsin requires an acidic pH, whereas your human amylase requires a neutral pH of 7, whereas your trypsin requires a pH at around 8 to 8.5. So it is around this pH this plays a role. So one factor which we heard about previously is the temperature, the next one is pH. Now coming to a different concept, which is the substrate concentration and the reaction rate. So the rate of the reaction increases as the substrate concentration increases at constant enzyme concentration. Okay, and the maximum activity occurs when the enzyme is saturated, that is when all the enzymes are binding your substrate. So here we can see that this is your concentration of the substrate and this is your initial reaction rate in moles liter inverse second inverse, because your enzymes follow the zero order kinetics, and sometimes first order kinetics. I will be coming to these later as to when and how, in what manner does they follow the different kinetics. Okay, so you see that when your enzyme is saturated, that is far more substrate than it can deal with. So in this case, so in the first case, your reaction is increases, and then it reaches a saturation level. Okay, and then and in terms of, so when that saturation level is reached for the enzyme, you can observe maximum activity. So maximum activity occurs when your enzyme is saturated, and also the rate of the reaction increases as your substrate concentration increases, but it reaches a saturation. So in the first stage, so in when see when so when your so at maximum velocity or at Vm, you are getting is maximum activity, and in this region all of the enzymes is combined with the substrate. You can see over here, so this is this stage, and then in this case your enzyme activity is increasing with your substrate concentration, and when this reaches a constant region or is totally saturated, you observe maximum activity. So now coming to the kinetics of the enzyme. So enzymes basically follow zero order kinetics when your substrate concentration is high. So what it means? So zero order means that there is no increase in the rate of the reaction when more amount of substrate is added. So it is not like that you are adding more and more and more and more amount of substrate that you are going to increase the rate of the reaction. So there is a saturation level which is reached at a certain point of time. But when the substrate concentration is very high, then you would be seeing that the enzymes follow your zero order kinetics. From the graph only you can see that zero order kinetics actually follows some kind of a straight line. So this straight line is attained when your so this straight line is attained when your substrate concentration is very high, at very higher concentration. But when your substrate concentration is low, it is following an exponential function or an exponential growth. Okay, so here you will see that your enzymes are following first order kinetics. So you need to remember one thing is that when your enzyme concentration is high, your substrate concentration is high, then you the enzymes are going to follow your first zero order kinetics, and when your substrate concentration is low, then your enzymes would be following first order kinetics. So here it is that it is a reaction between your glucose and between a sucrose and water, and this sucrose is a combination of your glucose and fructose. So in the presence of water, this is going to break to give you glucose and fructose. Okay. So this is the reaction. You have your enzyme, then you have your substrate, and this is in an equilibrium, your K1 and K minus 1, where your K1 is the rate constant for the forward reaction and your K minus 1 is the rate constant for the breakdown of your enzyme substrate complex to your substrate and your enzyme. And when this enzyme substrate moves to give you the enzyme and the product separately, that rate is called the rate constant for the formation of your products, or K2. So you need to keep this reaction in mind as we are going to proceed. So we see that when the substrate concentration becomes large, so enough to force the equilibrium to form completely, all the enzyme substrate, the second step of the reaction becomes the rate limiting, because no more enzyme substrate can be made and the enzyme substrate complex is at its maximum value. So if you break the reaction in terms of your enzyme substrate, that is dES by dt equals to your K1 ES minus K minus 1 ES minus K2 ES, and then you have the product that is your dP by dt, which is equals to K2 ES. So where your ES is the concentration difference between the rate of your enzyme substrate formation minus the rate of its disappearance. So what it says is that at higher substrate concentration, the ES, or the second step of your reaction, becomes your rate limiting step, because then no more enzyme substrates can be formed, because all the enzymes have been saturated with your substrate, and therefore no more enzyme substrates are going to be formed, and therefore the enzyme substrate complex reaches its maximum value. And another thing is that d of your ES by dt equals to your this equation, and your dP by dt equals to your K2 of your substrate concentration, and then we are going to derive the equation. So here we have an assumption of equilibrium is that K minus 1 is very large than K2. That is, the formation of product is so much slower than the formation of your enzyme substrate complex, that we can assume that your Ks, which is your dissociation constant for the enzyme substrate complex, is equal to your K minus 1 by K1, which is equals to your E concentration of your enzyme into your concentration of your substrate divided by your enzyme substrate concentration, complex concentration. Okay, so here we are assuming that your when the product is formed, that your product is forming at a very much slower rate than your complex. Okay, so then the dissociation constant of the ES becomes Ks, and you get this reaction. So this is another reaction which you need to keep in mind. And according to your steady state approximation or your assumption, we know that see, we have the enzyme and the substrate, and we require is the what is the enzyme and the product. That is, your substrate is getting converted to your product in terms of the enzyme, but in the middle you have a transition state or an intermediate product. Okay, so in the intermediate product you have your enzyme substrate complex, which you do not get in hand. So this intermediate step, we say that dES by dt equals to 0. So this is your steady state approximation. That is the transient phase where in the course of the reaction the concentration of the your product does not change. So here in that your concentration of the enzyme substrate complex is not changing, and this is your transient phase. So according to your steady state approximation, we can tell that see, your substrate is decreasing and your product is increasing, and your total enzyme concentration equals to your enzyme concentration plus your enzyme substrate complex. So in this case you can actually calculate the total amount of enzyme which you have. Okay, so from the steady state approximation, we are able to tell that dES by dt equals to your 0. And from the previously got equation, that is from this particular equation, we have to evaluate and find out the different conditions. Okay, so first thing that we need to keep in mind is this equation, which is a very important equation. The second important equation is your this equation, that is dES by dt, because from steady state approximation you need to actually evaluate and derive it. The next important equation is your Ks, which is equals to your Ki by K1, and finally from the steady state approximation you know that dES by dt equals to 0. So when we start evaluating it, and so this is mentioned that your total enzyme is equals to your enzyme concentration, that is your total enzyme is where your enzymes are actually present. So if you see from the previous graph is that your enzyme concentration is increasing when the reaction is occurring, and then it again starts increasing. First it decreases and then level is reached, and then it again increases. And the enzyme substrate complex, what happens is that it first increases, reaches a stable state, and then again decreases. When an enzyme is increasing, means your product formation has started and your complex has started decreasing. Okay, so means approximately we can tell that dEs by dt is 0. And so your total enzyme concentration will be your enzyme individually plus your enzyme plus substrate. And if you combine the three equations simultaneously, then you can actually get is what K1 into entirely your Et minus Es multiplied by a substrate concentration, which is equals to your K minus 1, that is your rate of the backward reaction in the first step, plus your K2 into your enzyme substrate complex. And when you rearrange them, when you start rearranging them, it is that when you get your K, you have to calculate it in terms of your intermediate product, that is your ES. So your ES into your K minus 1 plus K2 plus K1 into your substrate concentration. And this you can evaluate when you take it in, when you take this ES to that side and you keep the K1 over here. So you get what is this, and then you divide by K1 and solve for your enzyme substrate complex concentration, and there you get is ES equals to your ET into your substrate concentration, that is your total enzyme concentration, into your substrate concentration divided by your Km plus your substrate concentration. So your Km, so what is Km over here? So your Km is your K minus 1 plus K2 by K1. So this is another equilibrium concentration which you have. So this is an important equation which you need to keep in mind. So you can practice this at your home, is that by deriving this. This is not going to come, but there would be many questions and numericals based on these equations. So basically you have to keep this either keep these equations in mind, or you have to actually derive it, because deriving become is not much tough. You can practice at your home and try deriving these equations, then you would be able to understand them much better. And see, at V0, that is when your product concentration is 0, at that time the equation stands like this: your K2 equals K2 into yes concentration of your enzyme substrate complex, which is equals to your K2, your total enzyme concentration, your substrate concentration divided by your Km plus S. So where we got this from? We got this from this equation, this particular equation. And here your V0 is the initial velocity when the reaction is just starting out, and your Vmax is the maximum velocity. So at maximum velocity your K2 equals to so at maximum velocity it is equals to your K2 into your total enzyme concentration. Okay, now when you actually rearrange these all equations, you get in hand the most important equation which we need to definitely keep in mind, and there would be several numericals related to such an equation, that is your Michaelis-Menten equation. So when you go back, check the reactions and note it down, and then you actually combine all of them, you see that your initial velocity when your reaction is just starting or is about to start, it is equals to your maximum velocity into your substrate concentration divided by your Km, which I mentioned, which is equals to your K minus 1 plus K2 divided by K1, that is this, plus your substrate concentration. So this is a very important equation, and which you definitely need to keep in mind, and this is known as your Michaelis-Menten equation. And there are going to be many numericals, and surely there are going to be some numericals related to this particular equation. So V0 equals to Vmax into substrate concentration divided by K plus your substrate concentration. So here you see that you do not have your total enzyme concentration or the product concentration, nothing is there. What you require is the maximum velocity, and obviously in the maximum velocity you have different factors like your K2 and your total enzyme, but most of the times these values are constant values, and you would be getting you need to find out your substrate concentration or your Km value, which is important in finding out. So this equation is very important, and we would be deriving certain graphs based on this Michaelis-Menten equation also. So now from the previous graph, you see that with the increasing substrate concentration, it follows an exponential curve, and after you reach certain high levels of your substrate, it follows a straight line, because this enzyme substrate has become saturated and no more, and that is the maximum activity of the enzyme you can observe, that is your maximum velocity. Okay, so it increases. So this is your maximum velocity, this is your Vmax by 2, and at Vmax by 2 what you get is your gain. So how you get it? So when your V0 equals to your Vmax by 2, that means you get over here is half. Let me see if I can show you. So see, if your V naught equals to your Vmax by 2, which is equals to your Vmax into what you have is your substrate concentration, and divided by your Km okay. So what you have is this, and when you cut this Vmax and Vmax, what you get is half, so I take it over there, so you get Km plus your substrate concentration, which is equals to your okay. So you see at when your V naught V naught equals to your Vmax by 2, at that point your Km equals to your substrate concentration. You can keep this thing in mind. Okay, so from here we can understand that so from this we can actually tell that your at V naught equals to your Vmax by 2, your substrate concentration is Km. That's why we are getting these values. So these are not arbitrary values, is has been derived. So at Vmax by 2, your substrate concentration equals to Km because of this reason. So your Km is the substrate concentration where V0 equals to half of your Vmax. So from this graph you can understand. And your Km value varies widely among the different enzymes. So your Km equals to your K minus 1 plus K2 by K1. So now you can tell that, and previously as I have shown that Ks equals to your K minus 1 by K1. So now you can substitute this K minus 1 by K1 to your Ks. Okay, and then what you get is this, that Km equals to your Ks plus K2 by K1. So, and as this Ks value decreases, the affinity of the substrate increases. The K can be a measure of the substrate affinity if K2 is less than your K minus 1. So this is important, that with the increasing Ks value, your affinity will decrease, and with the decreasing Ks value, your affinity will increase. And you can, from the Km, you can measure the affinity of a substrate if your K2 less than that of your K minus 1. So we have reached half of our slides. I would be taking just 2 minutes of break, after which we can start over once again. Okay, so now in the previous slides we have seen that V naught equals to your Vmax into your substrate concentration divided by your Km plus your substrate concentration. So this is your double reciprocal plot where we have just reciprocated the uh, the units and all and the values and all, and we are getting here is that 1 by V naught equals your Km by Vmax into your 1 by substrate concentration plus 1 by Vmax, and then we are plotting it. So what we are getting here is the double reciprocal plot where we are plotting 1 by V0 versus your 1 by X, and you're having an intercept of your 1 by Vmax, and then we have a slope of Km by Vmax, and here at your 1 by substrate concentration it is meeting at the negative axis of -1 by Km. So when your V naught equals to your 0, at that your substrate concentration is equals to your minus Km. Okay. So from the line in the Lineweaver-Burke plot, we have the slope of which is equals to your Km by Vmax. So your Lineweaver-Burke plot is same as that of your double reciprocal plot, and here your 1 by V naught intercept is equals to your 1 by Vmax, that is the extrapolated x intercept, which is equals to your 1 minus 1 by K. So for small errors in low substrate concentration, it leads to large errors in your 1 by V naught value. And here what is most important is your K catalytic value, which is equals to your Vmax by your total enzyme concentration. So your total enzyme concentration equals to your enzyme concentration, your initial enzyme concentration plus the concentration of your enzyme substrate complex. So your Kcat is the number of reactions an enzyme can catalyze per second, which I said is known as the turnover number. So for the Michaelis-Menten kinetics, your K2 equals to your Kcat when your substrate concentration is very less than your Km, that is very little of your complex is being formed, and your initial enzyme concentration becomes equal to your total enzyme concentration, and your V naught is equals to your V2 by Km into your total enzyme concentration into your substrate concentration. So thereby you can also tell that your V naught equals to your K catalytic by Km into your enzyme concentration and your substrate concentration. So therefore we can tell that your Kcat by Km is the measure of your catalytic efficiency. So that is all we have to keep in mind for this thing. Next, what is another thing is your inhibition kinetics, is that there is a role of competition. There is a competition which is occurring. So it is a competition between the substrates. So when the inhibitor competes with the substrate, then what happens, and this is all. So basically there are three types of inhibitors. One is your competitive inhibitor, the other one is your mixed inhibitor, and lastly your uncompetitive inhibitor. So in your competitive inhibitor, so from the name you can understand that in your competitive inhibitor is that the inhibitor is competing with the substrate and all. And so here you can say, see that the succinate is in the presence of succinate dehydrogenase is forming fumarate, whereas when you change the substrate to malonate and use succinate dehydrogenase, then no such reaction is occurring. So this is your competitive inhibition. So the competitive inhibition, for your enzyme plus your substrate, you get your enzyme substrate complex and then your product, and you get the enzyme. But when this enzyme is in the presence of your inhibitor, that is you also have the substrate and the inhibitor, then you get your, then the enzyme actually binds to your inhibitor and your substrate is present, but your substrate cannot bind to such an enzyme, your enzyme, because it is already captured, the sites are captured by your inhibitor, and then no reaction is going to occur. So this is the entire thing of your competitive inhibition. And in the competitive inhibition, it is that the rate of reaction is that for the inhibitor, that is Ki, which is equals to your enzyme concentration into your inhibitor concentration divided by your enzyme inhibitor complex concentration. And your V0 equals to Vmax into your substrate concentration divided by a constant which is your alpha into Km plus your substrate concentration. So where your alpha equals to your 1 plus inhibitor concentration divided by your K. So this is a derived value. And so this is the your um, the derivation for your V naught value versus. And when you draw or plot your V naught versus your substrate, or 1 by V naught versus 1 by substrate, what you get over here, this is a plot of V naught versus your substrate. So previously we were seeing this graph. So previously we were seeing this where there was no inhibitor. Now as your alpha value increases, you will be seeing that this graph is having a lower of your V naught value. So with your increasing I, so when your I is increasing, the graph is becoming a much more less exponential and will become at one time a straight line. Okay. So your alpha equals to 1 plus inhibitor concentration divided by your Ki, when your alpha is 1, 2 and 4. So this is the graph of your V naught versus your substrate concentration. And at Vmax by 2, what you get is your Km value at your alpha 1. Okay, so at alpha, when your alpha is 1, that is when there is no inhibitor. So I have derived previously that Vmax by 2 equals to your Km value. I mean, at V naught equals to Vmax by 2, your Km equals to your substrate concentration, or vice versa. Your substrate concentration equals to your Km value. Now this is the Lineweaver-Burke plot, or your double reciprocal plot. Now when there was no inhibitor, you were getting just a straight line and all. But as your alpha value is increasing, you see that this is also increasing. Your alpha increasing, and this graph is becoming much more and more steeper. And this value, your 1 by Km, is becoming actually minus 1 by alpha Km. So as your alpha value is increasing, this the value is getting decreased, but your 1 by V naught value is getting increased, and your slope becomes alpha Km by Vmax. So here you need to remember is the intercept as well as your so you need to remember what happens at V naught equals to 0, and 1 by S value is your minus 1 by alpha Km. You need to remember the intercept, which is 1 by Vmax, and also your slope, which is equals to alpha Km by Vmax. So these are the three values which you need to keep in mind. Now in the terms of your uncompetitive inhibition, that is you're getting both. You're getting you have the enzyme substrate, you have the enzyme and the substrate, and your enzyme substrate complex is being formed. Now you have the inhibitor, and your inhibitor binds, and when your inhibitor binds, there is no reaction, but when your inhibitor does not bind, you get a reaction. So there is no competition as such. Only those which will bind to your inhibitor will not form the product, and which will not bind will give you the product. And this is your another Lineweaver-Burke plot, where your 1 by substrate concentration becomes your minus alpha naught by Km, and your intercept also changes over here to from 1 by Vmax to your alpha dash by Vmax, and your slope is remains the same as that when there is no inhibitor. So this is important, as I was saying, that slope equals to Km by Vmax, and then your intercept values changes from 1 by Vmax to your alpha naught by Vmax, and this value also changes to minus alpha naught by Km. So you see, with the increasing inhibitor concentration, you are getting higher values of your 1 by S at your 1 by V naught, when 1 by V naught equals to your 0. And coming to the last set of inhibition, that is your mixed inhibition, where you have the enzyme and the substrate, and your enzyme is binding to your inhibitor and also it is binding to your substrate complex. So the moment it binds to your substrate complex, you do not get any reaction, but when it binds to the enzyme, when it will the inhibitor is going to bind to your enzyme, in either way you are not going to get any kind of reaction as such, but it can happen that it is binding both to your enzyme and to the substrate. So when you actually try to derive it, so it is actually your slope becomes alpha km by Vmax, and your intercept becomes alpha alpha naught by Vmax, and your alpha, and when your V naught equals to your 0, then your substrate concentration, that is 1 by substrate concentration, becomes minus alpha dash by alpha km. Okay, so when there is no inhibitor, that time your alpha equals to alpha dash equals to 1. In this you would be having different values of your alpha and alpha dash. Okay, so here also you have the different values of your alpha and alpha dash. So with the increasing I concentration, you see that the intercepts are also changing, and at the same time you are getting also different values for your 1 by S, 1 by substrate concentration. And at the point when these all these lines are meeting, you get is 1 minus, so this point is 1 minus alpha dash by alpha minus 1 into km, and alpha minus alpha dash by alpha minus 1 into Vmax. So these are the points of your, these are the meeting points. And here your slope equals to alpha km by Vmax. Your intercept is alpha dash by Vmax, and this is your minus alpha dash by alpha km. So these are the three values which you need to keep in mind. And here your alpha equals to 1 plus inhibitor concentration by Ki, and your alpha dash equals to 1 plus inhibitor concentration by K dash I. Now mixed inhibition is when the inhibitor is binding to your enzyme at a location distinct from the substrate binding site. So the binding of the inhibitor will either alter your Km or your Vmax, or both of them. So your inhibitor, so the rate of reaction of the inhibitor equals to your enzyme concentration into your inhibitor concentration divided by your enzyme inhibitor complex, and your K dash I equals to your enzyme substrate complex concentration into your inhibitor concentration divided by your enzyme substrate inhibitor complex concentration, and your V naught becomes Vmax into your substrate concentration divided by your alpha Km plus alpha dash into substrate concentration, where your alpha dash equals to, as mentioned, 1 plus inhibitor concentration divided by your Ki dash. Now from the different types of inhibition we had, it is when there is no such inhibition is playing a role, that is no inhibitor is present, then your V max equals to remains your V max, and your K apparent M equals to your Km. But in terms of your competitive, V max remains V max and Km becomes alpha Km. Whereas for the uncompetitive, it becomes Vmax by alpha dash and Km by alpha dash. And for your mixed inhibition, it is Vmax by alpha dash and alpha Km by alpha dash, where your alpha equals to 1 plus inhibitor concentration divided by your Ki, and alpha dash equals to your 1 plus inhibitor concentration divided by K dash I. So that is all from the theory part. So now we have a few of the practice problems. So you would be solving first, and after which I would be discussing with you the answers. Okay. So what do we have? Okay, coming to the first question. So it says the site where the catalytic activity of the enzyme generally takes place is known as. Yes, so where the catalytic activity of the enzyme is So yes, the active site is the region where of the enzyme where the enzyme activity is taking place, and these I was mentioning also these things that these active sites can attain different shapes and structures depending on your substrate and all. So this would actually also help you in undergoing the different models which I was discussing with before, that the lock and key model or the induced fit model and all. So yes, so right answer is active site where your reaction is taking place. Now when the velocity of the enzyme activity is plotted versus your substrate concentration, which of the following shape is obtained? Parabolic, hyperbolic, straight line with positive slope, straight line with a negative slope. So what do we call such a plot of V naught versus your substrate concentration? Hyperbolic? Yes, that is right. So that is an hyperbolic type of a graph that we are getting. First it's an exponential, and then when it reaches constant, straight line is attained. So it is an hyperbolic way of actually plotting a graph, right? So 2B is the right answer. Okay, the next question is, given that the del G of the reaction is in equilibrium with P is negative in the direction of S to P. The reaction equilibrium favors the formation of which of the substances? So del G naught is negative. So what it will be, in which direction will the equilibrium shift to? When your del G naught is positive. Sorry, negative. Okay, so what happens when del G is negative? So you know that del G equals to del H minus T del S. It is that when your del G is negative, it is that your reaction becomes much more spontaneous and feasible. The reaction is feasible. But when your del G is positive, then there is difficulty in actually performing the reaction. It is why I'm telling you. So we discussed previously about the concept of free energy. See, if you see in this one, is that when your free energy of the reactant is greater than that of the product, then you see that a lesser amount of energy barrier is required to actually reach your product. And in this case, when your del G reaction is your reactant minus, your product minus the reaction, then you see that your product is at a lower energy, whereas the reactant is at a higher energy. So when you subtract this product from your reactant, you get the del G value as negative. Whereas when it is the vice versa case, that is your reactant is at a lower energy and your product is at a higher energy, your del G value is positive. And when this del G value is negative, then your reaction proceeds spontaneously, or it is a very feasible reaction. But for vice versa case, it is not true. So now when you have been asked that your del G value is negative, okay, so your del G value is negative for a reaction of S to P, and the reaction, and in which direction will the equilibrium shift? So now tell me, in which direction will the equilibrium shift? Because this is going to be a very favorable reaction. Then the product formation would be much more feasible, and you would be getting more of your products. So S will definitely be moving towards P in a greater extent, because your del G value is negative, so you would be getting more of your products, and S will shift towards P, so the equilibrium will be more shifted towards your P, and you would be getting the product, that is your P, in a much higher concentration. So the right answer is A, 3A. You got it? Why? Yes. Okay, good. Now the next question is for the reaction S plus E having an equilibrium to ES to E plus P, where S, E and P stands for substrate, enzyme and product respectively. The quantities that can be measured experimentally are. So what can you measure from these things? D, you say only the free product. See, if you see in my in the slides, I have mentioned different the different important equations. Okay, like I was saying the different equations which are very important. So the first equation is this, where V equals to dP by dt, where you can measure the enzyme substrate complex, and from this enzyme substrate complex and then your different assumptions and all, your steady state approximation, you can tell that dEs by dt equals to your 0, and then you are getting your enzyme substrate complex concentration, which is equals to your total enzyme concentration into your substrate concentration divided by Km plus your substrate concentration. And from here we are actually deriving your Michaelis-Menten equation, where you can also get your substrate concentration. Along with that, here you have Vmax, and Vmax defines your K2 into your total enzyme concentration. So you can measure the substrate concentration, you can measure the total enzyme concentration from this Michaelis-Menten equation. And definitely from the previous things you can understand that V naught equals your dP by dt. So definitely the product concentration would also can also be measured simultaneously. So now tell me what which is the correct option. Not only the free product, the free product can be measured definitely, but what else can be measured along with the free product? So you have the enzyme, yes. So the substrate can also be measured, which you can easily measure it. Then comes your product, and also the total enzyme concentration can be measured. So question number 4, A is the right option, where you can measure the substrate, product, and the total enzyme. Right. Coming to the next question, for a given enzymatic reaction, substrate plus enzyme equals to product plus X, which of the following best describes X? X is the substrate, X is the deformed substrate, X is the other form of the product, X is the enzyme itself. Yes. So what are the different steps of it? So first you have the enzyme with its active site. Now a substrate comes and binds to that active site, and then you get is the enzyme substrate complex. Means that you have the enzyme along with the enzyme plus substrate. Then these enzyme plus substrate, this substrate in the presence of the enzyme gets converted to your enzyme plus enzyme product complex. Now only when this enzyme product complex is formed, you get the product in its free form along with the enzyme. And also I was saying that enzyme is such a protein, and it varies from your chemical catalyst in a manner. Whether it has similarities along with the chemical catalyst, it does is that it does not have any direct role to play in the reaction. Rather, it reduces the activation energy of your reaction, thereby enhancing the rate of formation of your product. Therefore the enzyme does not get changed in any form, and substrate plus enzyme equals to your product plus your enzyme only. So X is the enzyme itself. So right, 5D is the right answer. Question number 6 is, to measure enzyme kinetics, which of the following is varied? Enzyme concentration, substrate concentration, product concentration, pH of the buffer in which the reaction is taking place. So what is the Michaelis-Menten equation telling? To measure enzyme kinetics, which of the following has to be varied? So these type of questions you can expect in your exams as well, because this is a part from which you can expect a lot of questions and a few numericals as well, where you would be given the different values of some of the constants and some of the variables, and you have to find the other variables. So this is a very important lecture which you definitely need to focus on, and you can expect a good number of questions from these. So tell me, what do we need to vary to measure enzyme kinetics? So this is a question from the Michaelis-Menten equation which I just showed. V naught equals to your Vmax into substrate concentration divided by your Km plus your substrate concentration. So now tell me, what do you have to vary? Is it Vmax, substrate concentration, Km, or your, oh, another one is also the substrate concentration and the initial velocity. Yes, so you need to vary your substrate concentration in order to actually measure your enzyme kinetics, because you see we have plotted its V naught versus your substrate concentration, and where you know that V naught is the initial velocity before the reaction has started, and your Vmax is the maximum velocity where your enzyme has reached the saturation level. So right, and by varying the substrate concentration you can actually measure the enzyme kinetics. But remember that there can be other type of questions as well from the Michaelis-Menten equation as well. In any way, 6B is the right answer. Which of the following determines substrate specificity of an enzyme? What determines the substrate specificity of an enzyme? So it is basically the complementary electrostatics of your substrate and enzyme that is actually playing a role. So what it does is that it accelerates the rate of the reaction. Also, another important thing over here is the complementary geometry of the substrate and the enzyme, because you can see from the previous two theories of lock and key model and your induced fit model, I was discussing that how this lock and key model is actually having a drawback, because there the enzyme cannot change the shape of its active site, therefore it limits the number of substrate it can actually, the number of substrates becomes limited which can bind to such a particular shape. So the complementary geometry of the substrate and the enzyme plays an important role, and also the electrostatics of the substrate and enzyme plays an important role, because they actually accelerate the rate of the reaction. So here both A and B are correct. So 7A and B both are the correct options. So if you have any difficulty in understanding, you can get back to my slides and read the theory of the theories of enzyme kinetics, which is the lock and key model and an induced fit model. Great. Okay. Now coming to question number 8. In Michaelis-Menten kinetics, Km is defined as, what is Km? Concentration of substrate required to reach maximum velocity, concentration of enzyme required to reach maximum velocity, concentration of substrate required to reach half of the maximum velocity, and concentration of the enzyme required to reach half of the maximum velocity. So what is Km? What is Km? What relation does it has with the substrate concentration? And does it have any relation with the concentration of the enzyme? That is actually you have to understand. Is it so? Let's get back to the graph. See, where is the graph? Let me find. Okay, see in this graph. Okay, now let's come to the derivation where I actually showed. Where do we have the derivation? See, your V naught equals to your Vmax into substrate concentration divided by Km plus substrate concentration. Now, when V naught equals to your Vmax by 2, okay, when V naught equals to your Vmax by 2, then what happens is that Vmax gets cancelled and it's half equals to your substrate concentration divided by Km plus substrate concentration. So Km plus substrate concentration equals to your 2 into substrate concentration. So at V naught equals to Vmax by 2, your Km equals to your substrate concentration. Okay, so what happens now? When Vmax becomes half, at that point your Km equals to your substrate concentration. Okay, so now coming to the question. So at V naught equals to Vmax by 2, your Km equals to your substrate concentration. That is what you need to keep in mind. Now the question says Km is defined as, you say, concentration of the substrate required to reach maximum velocity. Now tell me what is the correct answer. Yes. So the concentration of the substrate required to reach half of the maximum velocity. At that point, your Km equals to your substrate concentration. So 8C is the right answer. Good. Question number 9. The advantage of using Lineweaver-Burke plot is. What is the advantage of using Lineweaver-Burke plot? Or what are the advantages of using Lineweaver-Burke plot? Making it more easier. It's an MSQ question. Tell me. You can tell me, because I have said which of the values are actually important for these graphs, and in terms of competitive, mixed and different types of inhibitors, what are the values which are important. So you can tell which are actually important in remembering in terms of the Lineweaver-Burke plot. So what is happening? First of all, we are drawing a hyperbolic curve and then we are making a Lineweaver-Burke plot. So what is the first thing it is doing? Yes, it is definitely linearizing the Michaelis-Menten equation, because of which we are able to draw a straight line. Right, so A and B are correct because it is first of all linearizing the equation from a hyperbolic one to, and which is making us easier to draw a straight line. What else is correct? A and B are correct. What else is correct? Yes, A, B correct. There is another option which is correct. I was telling you to remember few of the values. One is slope, second one is the x-intercept, and the other one is the y-intercept. Right, so these values are also very important to remember. Let me take one graph out. Yes, so these are the three values. So where is it? Yes. So these are the three values which you have to keep in mind. So this is also an advantage of your Lineweaver-Burke plot. So what is it saying? Option D. The important parameters can be determined from the intercepts of your two axes. So from the two axes, what are the parameters which you can determine? One is your Km value. Okay. The other one is your Vmax value. And you know alpha value. From this you can calculate, or you are given a particular value. So from these intercepts you can get these particular parameters, right? So option A, B and D all are correct. So here no error things can be reduced or increased. So option C is incorrect over here. So for question number 9, the first thing is that it linearizes the Michaelis-Menten equation, because of which we are getting a straight line, and the important parameters can be determined from the intercepts of the two axes. Great. So A, B, D, all three are correct. Coming to the next one. In the Lineweaver-Burke plot, the y-intercept gives. Now tell me, what is the y-intercept in the Lineweaver's Burke plot? A very easy question. Which is the y-intercept? Yes, 1 by Vmax, I just showed you. So 10B is the right answer. What is question number 11 saying? For competitive inhibition, the maximum velocity can be obtained at... When can the maximum velocity be obtained? Increased enzyme concentration, increased substrate concentration, lower substrate concentration, and half of enzyme concentration. See, it is not always that you have to remember the equations, or if you forget the equations, then it's very difficult for you to actually give an answer. It is all that you have to use your brain and find out what is the question actually saying. So that will also actually help you in solving a lot of questions. So tell me, even if you do not remember the equation at the first instance or recollect it, tell me what happens. So what happens if you increase the enzyme concentration for a competitive inhibitor? So when you have the inhibitor as well as the substrate, so it is that your inhibitor is going to bind to your complex. So the moment you are increasing the enzyme concentration, the inhibitor will again go and bind to your enzyme. So the more you are increasing the enzyme, the more it will bind. So that is why the saturation level is not being able to be reached. So increasing the enzyme concentration won't actually help you. Rather, if you increase the substrate concentration, what it does, the more the number of substrate concentration is there, each of the enzyme substrate is going to form and give you a product, right? So actually what happens from your last Atelier principle is that every enzyme substrate complex is going to give you a product. So your enzyme substrate concentration concentration decreases, and the equilibrium will shift towards your product side, because it is actually giving you a product. So thereby, the moment you're increasing the substrate concentration, what happens? So the inhibitor gets replaced by your substrate, and the product formation becomes more and more feasible. So the maximum velocity can be obtained when you increase the substrate concentration. Clear? Okay, good. What happens during non-competitive inhibition? The inhibitor binds to the site which is called... Where does the inhibitor bind? So the active site is the one where the reaction is taking place. The binding site is the one where the substrate binds to the enzyme. So non-competitive inhibitor is that the inhibitor... Yes, at first instant it seems that it is the inhibition site, but is there any site called the inhibition site in the enzyme? So every enzyme is having an inhibitor site, and an inhibitor is coming and binding to it. Is it possible? No. See, so it is known as the allosteric site. Okay, so where the inhibitor is binding and your substrate is going and binding to the binding site, and or the active site, and the reaction is taking place, but your inhibitor is also binding because it is a non-competitive inhibition taking place, and therefore it is the allosteric site. Remember this thing, it is the allosteric site in terms of non-competitive inhibition, where your inhibitor is going and binding to your enzyme. So so for question number 12, B is the right answer. That is your allosteric site. Now with the increase in the concentration of the inhibitor, the Km value increases in case of... So when does the Km value increase? With the increasing concentration, when will the Km value increase? Competitive, non-competitive, irreversible or uncompetitive? I was just saying this. With increasing concentration, the inhibitor of the inhibitor, the Km value increases in the case of. No. Okay, so it is for the case of competitive inhibition. That is, when we are increasing the concentration of the inhibitor, what happens? More and more inhibitor is going and binding to your enzyme, and therefore the Km value is getting more and more increased. Okay, so go through the lectures, because these are the questions which you will be getting in your exams. And these are very important questions and very easy questions actually, because there is nothing to actually think about it. These are just basically direct questions. Basically, don't think I have any uh, numericals, but you can also expect a few numericals from these things as well. Okay, so for question number 13, it is A. For competitive inhibition, the with increase in the concentration of inhibitor, the Km value is actually increasing. Okay, coming to the last set, we have two questions. While monitoring the activity of enzyme in UV spectrometer, which two parameters are monitored in the instrument? Absorbance versus time. But read the axis as well. Absorbance in the x-axis versus time in the y-axis, or time in the x-axis and absorbance in the y-axis. Which do you feel is correct? Yes. So we plot the time in the x-axis and the absorbance in the y-axis. So these are easy questions, I understand, because mostly we learn is when we are plotting V naught versus C. It is that first V naught means it is in the y-axis, but you see substrate is in the x-axis. It's a very conventional that we would just jump into the solution without even seeing the axis. It's very obvious, but you have to go through it, because these are the very tricky and very easy questions. So but just not paying attention will actually cost you a marks. Yes, so D is the right answer. It's absorbance versus time, where your absorbance is in the y-axis and your time is in the x-axis. Right. So now the last question, question number 15. When a sliced apple is kept in open air, it becomes brownish, which is due to oxidation of phenolic compounds in apple by enzyme or diphenol oxidase. Yes, correct. It is because of the oxidation of the phenolic compounds in apple by the enzyme or diphenol oxidase. The other things are not true. Okay. So that is all with the questions and all. And when do you people have your exams? 29th of April, right? Okay. Okay, so go through these lectures. There are also, I would be uploading them in the YouTube. If you're having difficulties, you can go through these lectures and all. And okay, let's see how things go. Okay, so that's all from my part. Thank you.